Section 1.6, we are going to talk about transformations of functions. And in this section, we're going to take the function and move it up or down, left and right. We're going to stretch them and shrink them. We're going to reflect them on axis, and then we're going to call it a day, I guess. Wait, the class ends, we have 1 minute left and then another 40 after that, right? Good. So, let's see. We can shift functions. Transforming functions means shifting them left, right, up, down, and so on. So let's go with first shift up. Now I'm going to give you the overall formula which you should understand. It's f of x plus c, where c is larger than 0. So if you have a function that adds a number to the entire function, you are supposed to move that function that many units up. So let's have some examples immediately. Let's say you have the absolute value function, which is the v-shaped function, and this is y equals absolute x. If I want to shift this function, say 2 units up, and start at 2, and have an identical function, well, my formula has to look like this. Observe that the 2 was added to the entire absolute x function. So I'm just going to box every time we put a concept. Let's take a look at another example. Say you have a square root of x. Then you want to raise this how many units up? 1 unit up. So 1 unit up. The function has to look the same, but now it's y equals absolute x plus 1. No, what? Wait, that's a square root function. Why am I writing absolute? Square root of x and square root of x. So observe that plus 1 is not under the square root. It's to the side. The square root ends, and then plus 1. Earlier, you gave me the answer for x squared plus 2, which was shifted up 2 units. So you have that example from before. Let's shift down. What do you think? How do we shift down? Yes. So to shift down, we're going to have entire function, and then we're going to subtract a value from it. So, as an example, we're going to, let's take a parabola this time. Again, as I said, guys, this works for every single function under the sun. So we can just take x squared as the example now. And let's go 2 units down. So you will go at -2, and you will draw the same parabola. So this one is y equals x squared minus 2. Why is the stream offline? Didn't update yet. It's recording. So shift down is function minus c. So to move up or down, you go f of x plus minus c. Add a value, subtract a value. So now, let's go and shift to the right. This one is going to subtract the value directly from x. So it's f of x minus c. So observe the difference between shift down, which is function minus c, and shift right, which is x minus c. Example. So what should be our starting function? Anyone? Which function should I use? X cubed. Okay, thank you. I ran out of functions, that's why. So here's the x cubed function. And now we're going to move this how many units to the right? How many units? 2 units. So we have the same function as before, except it goes through 2, and observe y equals, open parenthesis, x minus 2 everything cubed. Now I don't want to convolute this on the lecture, on the tablet, so I'm just going to draw this on the board, and if you see it as important, you can draw this somewhere in the margin or so on. Guys, I have x cubed, which is what I just drew over there. Then I have x cubed going through 2, which is x minus 2 cubed. And then I have x cubed lifted up 2 units, which is x cubed plus 2. And then I have x cubed minus 2 right here. Observe the differences between these graphs and how they're written. Parentheses in mathematics are not there for decoration. All right? You have to use parentheses properly, and then hopefully by learning notation in this class, learning proper notation, you would know that this is the default function f of x. This is the function f of x, which is increased. It is x that was modified, so x minus 2 in this case. Over here you have f of x, which is x cubed, added 2. And over here you have f of x subtracted 2. So notation-wise, that c is the number that you're either adding or subtracting on the entire function to move up and down, or on x directly to move it left or right. And that's what we have for this shift. So it takes some time to get used to these and where they are and how they look like. So we're going to do another one now. If you deal with a square root, if the number is under square root along with x, then it's this situation and you move it left and right. If it's outside of the square root, like we had in the previous example, then depending on plus and minus, it's either shift up or shift down. Now also you're noticing here that the shift right has a minus sign and the shift left will have positive sign. So yeah, deal with that. Deal with that in your lives right now. Yes? It is actually, that is the default state, and the plus and minus, plus going up and minus going down, is the anomaly. Because we are going to learn, I know it makes no sense, but it does. So if you think about these things, we are going to learn a formula that will say, oh, it's almost invisible ink. Let me just get something better. So we are going to learn in chapter 2 a standard form for quadratics. And it's going to look like this. Y equals to x minus h squared plus k. And this h and k are going to be your vertex point, which is the tip of the either minimum or maximum for the parabola, and you will draw up or down. So that's chapter 2. Observe x minus h here. If you move k together with y, you will get y minus k is equal to ax minus h squared. And here it is. plus k on this side, which means plus k on this side goes up, but minus k on this side goes up as well, because they have to do the same thing. So actually, if the values of c are close to x, then they move left and right, and minus means right, plus means left. If they're close to y, then minus means up. But we usually have all of the stuff to the right. So that's why going up is going to be positive, going down is going to be negative when it's on the same side where the function is, and the x's are going to be backward. But in actual, world, both of them should be backwards, because this kind of shift up and down should be on the y side of the equation, and then minus would be up and plus would be down. There's going to be plenty of time for you to think about these things down the line as you take calculus and so on. Right now we're trying to focus on having always y alone so that we observe the function, because later on there's going to be implicit stuff in calculus and it's going to get a little bit confusing. So let's keep it simple, and you will memorize, literally memorize, that addition and subtraction on up and down, plus is up, minus is down, and you will also memorize that minus is right and plus is left, shift left for the next one. So let's do another example for shift to the right, which means negative. What do you want? What do you want? Rational, radical, absolute, square, cube? Absolute it is. So you see that the absolute value, absolute x, has the vertex, which is at the spike, right? At 0, 0. So that's our absolute x. How many units are you shifting this to the right? 3 units, thank you. So it goes 3 units to the right. And this is y equals absolute x minus 3, closed absolute. And that's 3. Now I'm going to draw something and then erase it. Just pay attention. Guys, every single point moved 3 units. You see, from this point here goes 1, 2, 3. From this point here, 1, 2, 3. Every single point on the line moved 3 units to the right. And later on, when we have those asymptotes, they move as well. So we have to be, hopefully you're understanding this. Let's shift left. To shift to the left, we have f of x plus c in parentheses. So let's go with the example, let's say square root of x. So now we know that we are not supposed to use negative numbers in square root, right? We talked about the domain in the last 2 classes. So if we talked about the domain in the last 2 classes, we know that we are not supposed to put square root of negative 2 and so on, because those answers are not real numbers. So now let's start with this one, which is the standard state, square root function. So this is just square root of x. And you can also see from the graph that if you put a negative 2, which is on this side, negative 2 does not intersect this graph anywhere to produce y value. That's why negative 2 is not in the domain. Get rid of that. But now what I can do is shift to the left. I can shift to the left, let's say, 4 units. By shifting the graph 4 units to the left, 1, 2, 3, 4, I will have exactly the same square root graph that starts at negative 4 now and goes on. Guys, negative 2 now works. So it's not that as soon as you see a square root function, negative numbers are out. You have to do this analysis now. Negative numbers are not out by default, because I'm just giving you an example now where negative 1, negative 2, negative 3, they just work just fine. Because when we look at this one, we know that our function is going to be square root of x plus 4. Shift to the left is plus inside square root. So this is the reason why negative 2 would work, negative 3 would work, right? You put the negative 3 in there, you get negative 3 plus 4 is positive 1. Square root of positive 1 is 1, which is this value here, 1. See how cool this stuff is? Come on. Where's the spirit? There we go. Sometimes, I feel alone in a classroom of 30. So occasionally I just want to hear your voice and, make sure that you're with me. So, yeah, that's the idea. You can shift functions up, down, left, and right, which will obviously start changing the domain and the range, right? And you see that in this case, the way for us to compute negative values inside the square root, we'll shift the square root function a little bit, and then we can include some of those. Cool? Of course it's cool, it's math. All right. Oh, you didn't expect that. Yeah, I say those things. Welcome to my class. Should we do one more to shift right or move along? Move along? Oh, right. Let's reflect upon x-axis and y-axis. Reflect on the y-axis. Do we remember the discussion on even and odd? Yeah, right there. A little bit of it. Everything is connected. All right, so we are looking into this and reflect over y-axis f of minus x. Well, immediately go with the example. So first of all, you should know by now, because you studied, I hope, even and odd functions, and you know that if I pick any of the even functions, like x squared, x to the fourth, and then some that you didn't learn, like cosine or secant functions, if you draw those as the example and you reflect them, they look the same, because they are symmetric on y-axis, which is exactly what the meaning of even functions is in regards to symmetry. So we can't pick that, but we can pick a good old square root function. Square root of x. And I want to reflect it on the y-axis. Well, that should be common sense that it's just going to be like in a mirror. It's going to go this way. And this is y equals square root of minus x. Now, let's just stop and admire how cool math is. Said it. The square root of positive 1 is 1. Square root of positive 4 is 2. Now look at this one. It only has negative numbers as the input. We can't plug in negative numbers. Yes, you can, because now you have an extra minus there, and minus will cancel out. So when you pick minus 1, you plug minus 1 in there, minus and minus cancel, you have square root of 1, square root of negative 1 will produce 1. If you plug negative 4 plugged in here, minus and minus give you plus, it becomes square root of 4 and produces 2. This is how cool this stuff is, right? So now with this transformation, I am able to replace what used to be only and exclusively positive numbers in domain into only and exclusively negative numbers in the domain, which is awesome. So now if you need to get some stuff from the negative line, negative x-axis, right, that can be used in this. The same stuff will work for logarithmic function later on. Same principle. So you will only work over positive numbers, and then you can use this minus to flip it on the other side if you need for some application or something. So reflection is as easy as just placing this minus sign glued directly to x, not to entire function, just directly to x. Let's take a look at another function. So what would be another cool example? How about, okay, we're going to do one cool example, and then we're going to do something that confuses the hell out of like 90% of population. So you don't make those mistakes later on. I don't, yeah. Trust me, I've been teaching this class for over 70 years, all over the world. So how about, what would be a cool function to use? X to the fifth. Thank you. That's awesome. So we're going to learn in chapter 2 that all of the odd exponent functions, so x, x cubed, x to the fifth, x to the seventh, x to the ninth, and so on, so odd number, all of them should start in the left-hand side, right, in a third quadrant, go through 0, and then emerge on the first quadrant and go up and to the right. As you start increasing exponent, the function will tend to hang around longer around 0 where it crosses the x-axis. So if you are to draw, I'm going to draw x cubed and this one, and then I'm going to erase x cubed. So x cubed, if x cubed does this, then x to the fifth will get closer and then live longer around x-axis and then disappear. So you can see that there is this region here where the function hangs around x-axis longer than that x cubed. And if you want to draw 7th degree and 9th degree and 11th degree, you will just start and then let it sit longer and then emerge and so on. So the higher the degree, it hangs longer around the x-intercept, around x-axis. So this is your x to the 5. And we are going to reflect this now on the y-axis. And when I reflect this on y-axis, it's going to do exactly the opposite. So it's going to come in this side and go down. And this is going to be y equals. And then you have negative x to the fifth like this. So minus sign is applied directly to x. Now, one thing that we know is that this minus can actually, because there are 5 of these, they combine into one minus outside. So we'll discuss that once we do the other transformation as well. What I want to work on now on the side is this confusing situation and try to explain it so that there are no issues. I said I'm not writing your final, right? I said that because it's assessment here? Good. So whatever is there, you solve. And I need to make sure that if this stuff pops up, you guys know what's going on. So y is equal to x squared, and we all know this. Now this is your y-axis in the middle. What's going to happen with this function as I reflect it on y-axis? It's going to stay the same. Now can we see that from algebraic, from the formula, rather than just looking at the image and then trying to flip and then realize that? And the answer is yes, we can. Y is equal to negative x everything squared. Now what happens with the minus? Right? Minus times minus is positive, so this is the same as x squared. Now guys, this is your definition for even functions. Every even function will have this feature. X to the 4th, x to the 6th, x to the 8th. And then also cosine and cosecant, secant, and then some other functions down the line, like hyperbolic cosine. So we're going to have the functions that are even, and for even functions, this feature will be there, and you will get to see that this transformation, when applied, leaves the function in the same state, right? So it looks the same. And cool thing is that you can actually see that from your calculations, from canceling. And then the next part would be reflect over x-axis, which is going to introduce the minus sign on the entire function. So, immediately with the example, we haven't used absolute value for a long time now. And if I'm reflecting this one on x-axis, what's happening? Flip upside down, so these two are going downwards now. Observe that the minus sign is outside. Oh, by the way, the absolute value function is one of the even functions as well, right? You see that? And you know that if you apply the minus directly on x, the absolute value is going to kill it. Right? It's cool. It works every time. No exceptions in mathematics, ever. Would you agree that this is easier to learn than language?
Yeah.
Yeah, completely, right? See, when I moved in to US, it took me some time to learn the exceptions because we don't have deers. I used to say deers for a long time. Popcorns, right? No, it's popcorn. You get a bunch of them, but there's no S at the end, which is for plural, right? You put S at the end. So there are exceptions to learning a language, and that's why it gets to be so annoying, right? Or in this case, look, one rule, you learn that rule, it applies to all mathematics. Thousands of functions. Behave the same way under that minus sign. Is it inside or outside, right? And if you know that one rule, it applies to all, no exceptions. You will never find an exception in mathematics, anywhere. It is a rule that you either learned or ignored, which means you can do it or you can't. There is no maybe. There's no gray areas or anything like that. It is, everything is perfectly defined and at all times perfectly fits. And everything that you skip hurts you later. So you just saw that I connected all of this to even and odd functions, and then I told you that all of this is going to be recycled over and over again down the line. So yeah, learn it. Should we do, let's do x cubed, because we can. Right? Is anyone going to comment on this example? Anything? Look at the x cubed. So we reflected it on x-axis, right? Reflect on the x-axis. So, aha! Awesome. So we did reflection on the x-axis, but then at the same time it looks like we did the reflection on the y-axis. You can't actually tell, if I put these two next to each other, you can't tell, or you can equally argue that the reflection was done either on x or on y. Right? So you're looking at this and say, well, which one is it? Both. Why? Because math, exactly. Because math. All right, so what do we have? We start with y equal x cubed, and that's our default state, right here. If I decide to reflect on a y-axis, sorry, x-axis, I have this. And that's the graph that I have there. So the minus sign applied to the entire function. And since exponent goes first, right, so a cube is glued to this, you don't need parentheses. You don't need these parentheses around, because the cube will be applied first anyway. But if you reflect on the other one, you get this. But what do we know? This is negative x times negative x times negative x, which is, again, this, right? 3 negatives make negative and negative is positive, and another negative is that negative. So you actually get the end, same thing. So here is your default state, reflect on x, reflect on y, which is, again, the same thing like here. So if you get these two graphs, you can't really tell. But it doesn't matter, you pick one. Why? Because function is odd, and it's symmetric to the origin. Symmetry to the origin means symmetric on x and y-axis at the same time. Awesome. So there you have it. So we covered 6, 4 to go. Because we can stretch function, right? Look. Right? Awesome. That's what I'm going to do tonight when I get home. Have some cake. Rafael, was it 2 years ago when Shannon ordered the shirts? Yeah, okay. So for Order Up Club, we ordered these shirts. They're awesome shirts. Good quality. Nice bag, right? It's like, yeah, we got it. We can order every year, except last year we didn't. So for whatever reason, every single size they will send in came in one size higher. But it still said the original size, right? So if I ordered large, it would still say large, but it was actually extra large. So everyone across the board. Well, that's an easy problem to fix, right? You don't want it the other way around. You can grow into clothes, but the other way around is hard, right? And you gotta do hard work, which is not fun. Right? Exactly. More cake, you're good to go. What else? What else are we gonna do now? Let's stretch functions and shrink functions, and we're going to do that horizontally and vertically. So now, we're going to take the function, whatever it is, and just stretch it like this. So it's going to go up. And we do that by multiplying the entire function by a constant c in front. So c times f of x. And if that c is bigger than 1, it's going to go whoop. And if it's a fraction, it's going to squish it and kind of try to flatten it. So what do we have? 3 minutes and then another 5 after that. Good. We have time. Let's see. So I have to write these in the same, so it's going to be only 2 lines, but actually there are 4 things happening, but only 2 will be written down. So let's go with the vertical. Stretch or shrink. And that's done by c times f of x. You stretch things when c is bigger than 1 or smaller than -1, and you shrink things when c is in between -1 and 1. So clearly, if you're multiplying something by a half, you're cutting thing in half, right? So it's going to be shrink. If you multiply something by 10, you just made it 10 times larger. So that's going to be stretch. So please use common sense at all times. Now, the interesting thing is that the best way to describe this is to use trigonometric functions, which are covered next year. But your textbook, right, uses the trigonometric functions to describe this anyway. So we'll be fine. They don't give you the formulas. I will, because I'm awesome. So here we go. I'm going to draw a basic sine function in its original state. So it starts at 0, 0, goes into 1, and then drops to 0, goes to -1, and then climbs up. And this is known as sine x. And you will learn this next semester. Now I'm going to take the function sine x and multiply it by 2. It is going to actually, and I'm going to draw on the same graph. So what's going to do, it's going to go up to 2, fall down to 0, go down to -2, and fall up, and that's going to be 2 sine x. I hope you guys see that vertical stretch. Now, sine function is a wave, and you can literally think of this as waves of the ocean, right? Where you have a 1 foot wave in the original state, and then the red state is 2 feet tall, so it's 2 foot wave, all right? We can also shrink. So that was a stretch. Let's shrink. So now I'm going to use, let's say, 2 units to be 1 unit, so it's easier to see. Oops. So start here, 2 units, 2 units, 2 units, 2 units, x, the y. I'm going to connect the sign again. And then I'm going to cut it in half. So the black function is good old y equals sine x, and the blue function is the one that is shrunk, which is 1/2 sine x. So vertical stretching and shrinking is done by simply multiplying the function by a number in front of that function. Now we can also exercise this with the square root, let's say. Blessings. So this is your square root of x. And this is your 2 square root of x. So it gets stretched up. And so on. So there are a whole bunch of examples that you can do. Obviously the blue line, draw the blue line as well, why not? Here we go. 1/2 square root of x. Now if you shrink, all 3 on the same graph. But they're color coded, so. Now let's make some mathematical connections. Remember that graphs are all about figuring out the y values for given x values. So if I draw anywhere over here a vertical line and say that this black one is 1 unit, then, well, the red one is drawn bad, but you know, this one and then twice that size. So the red one should actually go much higher. And then this one should be 1/2, which is. So at least I got the blue one right. So if this is the y value at whatever this x value here is, if that is the y value for it, then 1/2 of that y value has to be half the distance, right? So it should be some just common sense on the graph. And then the red one should go, you take this distance up there, so the red one should actually go to here. It should go like, the red one should go like this. To be more realistic. But such like. So that's the vertical stretching and shrinking. And now we have, what do we have? 1 minute left and then another 2 after that. So we have time. We go with horizontal stretching and shrinking. Which is f of, and then c times x in parentheses. And now, we're still going to use, your book use it as well, trigonometric function to explain the concept, and then we're going to try and find some function that would work nicely from our assortment of functions in Precalc1. Let's start with, this time with cosine, because we can. So every 2 units something special happens. We go down into here, we go up and there. And then that's x, and then that's y. So this black function here is known as the cosine x. And now what I'm going to do is I'm going to make the cosine x stretch. And what I'm going to do now is I'm going to move this point here, this point here, here, I think it's here. Wait. Nope, 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 I miscounted. So the top function, I want this one. That was a quick reboot. So I need 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That's where the end is. And then at the 4 it's this one, and then in the middle of these, right there. Well, I had it right. So this one over here is going to be cosine of 1/2 x. And then if I draw the same cosine for the shrink, and then make it go twice as fast. So this will be cosine 2x. So this is how your Precalc 2 is going to look like, except you're going to do much more with these things. The shrink and the stretch are best shown on the trigonometric functions, so that's why the book uses it and I use it in class. So those are all 6 transformations. You have horizontal and vertical shifts, horizontal and vertical stretch and shrink, and then you have the reflections on x and y. Now, the best problems here are going to be covered next class. We don't have time for it now, but when you start combining a whole bunch of these, so you take shift up and then vertical stretch and the reflection on y-axis, for instance. So we're going to deal with those types of problems next class. You should start working on the homework, and then I will see you all on Thursday to finish 1/6. We'll do 1/7, try to push into 1/8, try to catch up a little bit.
What chapters do you want?